too much, but I'm going to just cram the entire course into the next couple slides. So I teach computer graphics here at Cal Poly, the computer science department. And that's usually I'll see you, hopefully, some of you when you're sophomores, but more likely when you're juniors and seniors. And as all of you know, computer graphics is great, and in particular, 3D computer graphics is fantastic. How many of us saw 3D movies, right? Right? Okay, so I first saw 3D displays about 15 years ago when I worked at NASA. They were using a 3D visual display to work on some of the aerodynamics of their airplanes, and I was like, that's so cool, why did I like it? So why do you like it? You like it because the biggest system in your brain is designed to analyze visual images. That means your brain is mostly working on analyzing the world around it visually. So in particular, humans have a very particularly interesting vision system. We have the vision system of a predator. We don't have two eyes on the side of our head to see all around us. We have eyes in front of our head so that we have two overlapping views of the world, which gives us 3D vision. So what is 3D? You can talk about it mathematically. We can talk about 3 axes, X, Y, and Z. But really what we care about is we care about depth. So we care about how far away is something from where I am right now. And it turns out that having those two eyes in front of your head with two slightly displaced images, your brain is constantly doing tons of trigonometry to solve for the depth of objects given those two different viewpoints. It's triangulating and solving for depth continuously. The depth perception is so important that even if you don't only just have binocular cues from the two eyes, but you have a lot of monocular cues. That means with just one eye or one picture, like with Cezanne, you can perceive depth and understand from a single image how far away things are supposed to be. Some of those fun monocular cues is motion parallax. This is a fun one. You cover one eye and move your head back and forth. Objects that are closer to you move more in your view than objects that are further away. There's also things like perspective and occlusion. So if something is blocking you, that thing is obviously closer. There's also relative size. You have objects that are about the same size, like a car. If in your view one of those objects is smaller or bigger, you have the ability to compute that the object that is smaller is further away, and in fact, if you understand its size, pretty much how far away it is. There's also things like aerial perspective. If you're outside, things that are foggier, we can interpret as further away, and even color, where warm colors are perceived as being closer to you, and blue colors are perceived as being further away. Artists have used all these techniques with a single image to have you be able to perceive depth. You put that all together, and you get, that's why we like computer graphics and 3D displays, because a huge part of our brain is dedicated to processing these visual images and to understand how far away things are, understand 3D. So quickly, how do we fake this? Okay, so our job in computer graphics is we have some 3D definition of the world, but ultimately we just have to display it in 2D on a screen. That's our job. That's what we do in computer graphics. So the first thing you have to do is you have to define that 3D world. So we can define it mathematically. We can think about some big list of points that have some X, Y, and Z coordinate, and they have some connectivity relationship to one another that determines how they're connected that can form a 2D surface embedded in 3D. Typically they're triangle meshes just because the hardware is optimized for that. So you have a huge 3D world that's defined, and then we need a mathematical definition of a virtual camera in that 3D space, because that virtual camera is going to allow us to simulate a projection onto 2D so that I can create images. So I can create two images that simulate the two images you would see for a left and right eye. By using some glasses, I can help the correct eye see the correct image at the right time, and then your brain will do all that trigonometry work that it needs to do in order to compute the depth from those two displaced images. So let's go back to this question about how do we actually get those 2D images. So ultimately, that 2D image in computer science is just a pixel. It's a bunch of pixels, these little 2D finite images, finite elements that we need to decide how to color. We can decide how to color them using all those monocular cues that our brain is already doing and that artists have been doing for centuries. Mostly we have to respect perspective, relative size, and occlusion in order to come up with those correct images for our brain to compute 3D. So it turns out that linear algebra is one of the ways that we can actually do all of those. So all of you should take linear algebra. 4x4 matrix transforms gives us almost all of computer graphics and some trigonometry. So by using some careful mathematics, we can follow those rules of perspective, and then likewise we can do some sort of data housekeeping stuff. That's another thing we do in computer science. in order to keep track of which objects are closer to the camera, so that when I'm painting my pixels to decide what color they are, I will color it with the object that is closest to the camera. And then likewise, I can do some vector math in order to determine what color that pixel should be, in order so that I can shade it correctly, so that shading hues can give us depth. Because we need to understand whether an object is pointed towards a light or away from a light, and that's some vector math, so vector math is also good. You put that all together though, and we get 3D graphics, which is awesome for both fun and for science.